In addition to having explicit formulas for characters, of course, we could also have generating functions for characters. Now, these involve a polynomial ring and n-squared variables. So let's look at that polynomial ring and actions of the symmetric group on it. First of all, let's think about generating functions as we normally think about them. So generating function, a natural generating function for a function f from the natural numbers to anywhere, let's say the complex numbers, is the sum as n goes from 0 to infinity f of n x to the n. So f of 0 plus f of 1 x plus f of 2 x squared, etc. We put f of n next to f x to the n just to have a place to hold it. Similarly, a natural generating function for a function f from n cross n to the complex numbers, or really anywhere, is we want to record f of mn somewhere, so why don't we put it next to x to the m, y to the n. So this will be f of 0, 0 plus f of 1, 0 x plus f of 0, 1 y plus f of 1, 1 xy, etc. Put f of m n next to x to the m, y to the n, just a place to hold this value. Now, a natural generating function for a function theta from the symmetric group anywhere, let's say to the complex numbers, is, now we want to put theta of w next to some kind of monomial that reminds us of the permutation w. So if we have enough variables, and squared variables in particular, then we can form this permutation monomial where the first indices are 1 through n in order, and the second indices are some permutation of n. Now here, I mean x rather than a single variable, I mean x is now a matrix of variables, xij, where ij are anywhere between 1 and n. So x11, x12, etc. up to x1n, x21, x22 up to x2n, and the last row is xn1, xn2 up to xnn. So I'm going to call this matrix just x. So some functions from the symmetric group to the complex numbers we might be interested in are the irreducible characters and induced sign characters and induced trivial characters. So we might ask, are there nice expressions for, so this function I should write, it's called the theta immanent. just a generating function for theta. The word imminent was first used by Littlewood. I'm not sure why he came up with that word. So it's a generating function for theta. So we could look for generating functions for irreducible characters, generating functions for induced trivial characters, and generating functions for induced sign characters. Now, the answers are yes, yes, and sort of when we get to irreducible characters. I'll let you decide whether the generating function that we know is nice or not. Let's look at an action of the symmetric group on this polynomial ring. So this polynomial ring is based on a matrix that has n squared variables. So maybe let's look at a slightly simpler action of Sn on the space of n by n matrices. So Sn acts on the space of all n by n matrices by letting the generator little si be the linear map so Si is going to take an n by n matrix to an n by n matrix just by multiplying by its permutation matrix on the left. Now this permutation matrix is not actually the matrix representing Si because A belongs to n by n matrices, which is an n squared dimensional space. So we really have to sort of unwrap the matrix A and make it a long n squared long vector. And then there would be another matrix representing this action right here. I'll just write this is an n squared dimensional representation. All right, now let's let C bracket x be C bracket x11, x12, etc. up to xnn. Now Sn acts on C bracket x by letting Si be the linear map. Si takes a polynomial in n squared variables and gives us another polynomial in n squared variables. In particular, it maps f of x, x being n squared variables, to f of, we'll apply the permutation matrix of Si to x, and then apply f to that matrix. So this is going to swap rows I and I plus 1 of the matrix, and then we'll apply f to the resulting matrix. Now this is an infinite dimensional representation. And we really only need, well, I've erased it, monomials of degree n, and not even all monomials of degree n, but just the ones that have all possible row indices and all possible column indices. So the permutation monomials. So let's let V be the subspace consisting of those permutation monomials. And let me abbreviate this monomial because it's sort of cumbersome to write it that way every time. X, E, W. More generally, let me write X, V, W to be the monomial where we have row indices V1 through Vn and column indices W1 through Wn. So I used E here because the first indices are 1 through n. So the dimension of the space we're looking at is n factorial. And these variables commute, so we can express everything in terms of this basis, x1 something, x2 something, etc., up to xn something. So XEW for W in Sn is a basis. All right, let's look at how S acts on this subspace V. So the subspace is going to inherit an action from the action of Sn on the whole ring. So Si is going to be the linear map taking f of x to f p of Si x. And I think the easiest way to say it is x e w to x e s I w. So to see that, let's let f of x be the function x e w. Then f of permutation matrix of Si x equals permutation matrix of Si x, whatever that matrix is, the product of entries corresponding to EW. So P S of I x is now in row I, after we multiply by the matrix P of Si, we're going to see the variables that used to be in row I plus 1. And then in row I plus 1, we're going to see the variables that used to be in row I. All right, what happens when we take the product of entries where the row indices are 1 through n in order and the column indices are w1 through wn? So we take something from the first row, in particular the W1 entry of the first row, and the W2 entry of the second row. Then when we get to the ith row, we're going to take the Wi entry of that. But the ith row has variables that used to be in the I plus first row. So we're going to take the variable xi plus 1 wi. And then after that, we're going to take the variable xi, wi plus 1, and then everything else will be what it should be. Now these variables commute, so what we have is, we'll write this one first, xi, wi plus 1, xi plus 1, wi. So now that the row indices are all in order, we see that the column indices, the second indices, are exactly w except for wi and wi plus 1 have been swapped. So we get SIW. Thus the formula here. Now, as I said, whatever monomial we have, if all the row indices appear exactly once and all the column indices appear exactly once, we can express that as a basis element, actually. Not just a linear combination of basis elements, but it will be a basis element. In particular, xvw equals xev inverse w. And I'll leave that as an exercise for homework. Now in expressing the generating functions in simple ways, we're going to use submatrices of this matrix X. In particular, for J, a subset of 1 through n, we'll define xjj. Actually, more generally, for two subsets of 1 through n, let's say capital I and capital J, we'll define x capital I, capital J to be the submatrix consisting of rows in capital I and columns in capital J. So if I write x1324, I'm going to omit the curly braces and commas here. This is the set 1, 3 and the set 2, 4. This is going to be a 2 by 2 matrix where we're looking at rows 1 and 3 and columns 2 and 4. So it'll be this 2 by 2 submatrix. And actually, I'm mostly going to be looking at row sets and column sets being the same, but I might as well put the full definition up here. The end.